In this class, we will introduce some formulas that help us calculate probability in more complicated scenarios. Recall the basic formula for calculating probabilities. Suppose an experiment has n possible outcomes. An event E has f outcomes. Then the probability of the event E is f divided by n, or the number of outcomes in the event E divided by the total possible outcomes of the experiment. We have discussed some operators of event, including not, and, or. In order to calculate the probabilities of this event, there are two possible approaches. First one, we first identify the event not E, A and B, A or C. Count how many outcomes in each event, and then apply the above formula to calculate probabilities. Second one, we can express this probability in terms of probability of E, probability of A, probability of B. In practice, which approach to use depends on what information is available and which approach is easier. The first formula is applicable when event A and B are mutually exclusive. In this case, if we want to calculate probability of A or B, we can directly calculate the sum of probability of A and probability of B. We can explain this formula in terms of the Venn diagram. When events A and B are mutually exclusive, they are disjoint, which are represented by the two separated circles in the diagram. Because A and B have no outcome in common, the event A or B is exactly obtained by combining outcomes in A and outcomes in B together. Hence, the number of outcomes in A or B is thus equal to the number of outcomes in A plus the number of outcomes in B. To get the probability, we divide the number of outcomes by the total number of outcomes in the experiments. Therefore, we obtain the formula displayed in the slide. This formula can be further extended if we have more than two events, A, B, C, and they are mutually exclusive. The probability of A or B or C is therefore the sum of the probabilities of all these events. Look at this example. Consider the experiment of randomly selecting a farm in the United States. The table shows the relative frequency of the size of farms, which are essentially the probability of farms of different sizes. We use letter A to G to denote different size of farms. The question is, what is the probability that a randomly selected farm has between 180 and 1999 eggs exclusive? The first step is to represent the event we are interested in terms of A, B up to G. By looking at this table, we can see that the size between 180 and 1999 corresponds to event D, F, G combined. Or in terms of mathematics, we say that the event that the size falls between 180 and 1999 equals to D or E or F. Clearly, by the definition of D, E, F, they are mutually exclusive. We can apply the formula of the special addition rule. This probability is the sum of probability of D, probability of E, probability of F, or 0.167 plus 0.068 plus 0.042 equals 0.277. Now let us check what the complementation rule is. This rule is used to connect the probability of not E with the probability of E. For any event E, the sample space can be partitioned to E and not E. Notice that E and not E are mutually exclusive. Hence, we can apply the special addition rule we just described. Probability of sample space equals probability of E plus probability of not E. Notice that the sample space is a sure event with probability 1. Hence, probability of E plus probability of not E equals 1, or probability of E equals 1 minus probability not E. This formula is called the complementation rule. We can use it to calculate the probability of an event from the probability of its complement. Let's consider again the experiment of randomly selecting a farm in the United States. What is the probability that a randomly selected farm has less than 2,000 eggs? Check the table. Less than 2,000 eggs means events A or B or C or D or E or F. If we consider its complement, less than 2,000 eggs means not 2,000 or larger, or not E. Applying the complementation rule, the probability of less than 2,000 is equal to 1 minus the probability of 2,000 or larger, which is 1 minus 0.036 equals 0.964. Of course, equivalently, we can still work out this problem using the special addition rule. We can add the probabilities of event A, B, C, D, E, F together, which leads to the same answer, 0.964. This problem can be solved using either the complementation rule or the special addition rule. However, the complementation rule is easier for this problem. The special addition rule is only applicable when two events are mutually exclusive. When they are not, we need a different formula. If A and B are any two events, no matter whether they are mutually exclusive or not, the probability of A and B equals to the sum of probability of A and probability of B, subtract the probability of A and B. This formula can be explained using the diagram below. Notice that A or B means all areas covered by both circles A and B, including the green, red, and yellow areas. Event A corresponds to the green and red areas, where event B corresponds to both the yellow and the red areas. When we add probability of A and probability of B together, the red area, which is common to A and B, are counted twice. Therefore, to make the relationship hold, we need to subtract the common red area, which is A and B. This formula also includes the special addition formula as a special case. When A and B are mutually exclusive, A and B is empty, or probability of A and B equals 0. In this case, we have probability A or B equals probability of A plus probability of B. In the bottom diagram, we can see that there is no red area because A and B have no outcome in common. Consider the experiment of randomly selecting one card from a deck of 52 playing cards. Let event C be spade cards. Let event D be face cards. In order to calculate the probability of C or D, we can calculate it as probability of C plus probability of D minus probability C and D. We need to figure out each probability one by one. Event C contains 13 spade cards, and the probability of C equals 13 over 52. Event D contains 12 face cards, and the probability of D equals 12 over 52. Event C and D means spade face cards, or Jack, Queen, King of spades. It has only 3 cards, therefore probability of C and D equals 3 over 52. Plug in the numbers to the formula, we get 22 over 52, or approximately 0.4263. Of course, we can use a different approach, that is, directly find out the event C or D. It contains 22 cards in total, and probability C or D equals 22 over 52, which leads to the same answer. In practice, which approach to use depends on what information is available and which approach is easier.